Hello, everybody. I'm happy to be on the Vaxjo conference, even though in such a format. I bet you're having a great time listening to the great lectures and talks, eating good food and enjoying hospitality by Andre. I envy you very much. So, today I want to add to my poster a little video explaining how we can create a two-block sphere model to represent all of the two-qubit states. And this model, I think, highlights some interesting geometric properties of entanglement. Let's see. When I speak about Bloch sphere, we know about general vector on the Bloch sphere. There's coordinate axis, and there's the sphere. Well, when I'll be speaking just for the pictures not to be so messy, I won't be using the sphere itself. So I will be using notation like this, where there's no sphere, but there's only coordinate axes, x, y, and z, and the arrow for the state itself. Yes, so now to the talk. We can represent all of the states of a single qubit state, on a single Bloch sphere. Yes, we just draw the arrows and we get all of the possible pure states of the single qubit state in this way. So basically what we're saying is that Hilbert space of a qubit can be projected into 3D space, into 3D Euclidean space. But there is a problem when we are trying to do the same thing with two qubit states. As with two qubit states, the problem is that Hilbert space of a compound system is not the same as just 2 times Hilbert space of a qubit, and therefore we can represent using our arrows only the separable states. Yes, we can use two Bloch sphere model to represent separable states. For example, we can use like state up for the qubit. We can draw it in this way, and it's easy. We can draw any other separable state of two qubits using two Bloch spheres, but we cannot draw entangled states or maximally entangled states. If we were able to do that, we could superpose two pictures of entangled and non-entangled and have all of the states which are in between. So the problem and the main goal for this work is to figure out how to still use only two Bloch spheres, but to represent also the maximally entangled states on them. And in order to do that, we will use some properties that are implicit in our description of the Bloch sphere, namely the coordinate frames. But first, we should remember that single particle density matrix of a maximally entangled state, for example, psi plus state, a single particle density matrix is identity. So it's 1, 0, this, which graphically means that there is no arrow but only a dot in the middle of the Bloch sphere. So that's one of the properties we want our geometric formalism to show, is that we want for the maximally entangled state, there won't be a state arrow, that there would be just a dot in the middle of the Bloch sphere. And the second property, the main thing of this talk actually, is that we will use for depiction of entangled state relationships between the coordinate axes of the Bloch spheres. Basically, we want one of the Bloch spheres to have different-handed coordinate frames. So we want to have one of the Bloch spheres different-handed, left-handed coordinate frames. So basically, maximally entangled states, that's the punchline of this talk, are representable by Bloch spheres with different-handedness of their coordinate axes. That's it. Now how we can represent some of the states. Here are the examples. Psi plus, we invert the z-axis. Now we invert the z-axis and we get the psi plus. Actually, there's 4 ways to invert to get to move from the initial picture that we had before with two Bloch spheres to the final entangled states. Yes, we can invert z-axis, we can invert y-axis, we can invert x-axis to get the left-handed coordinate frames, and we can invert all of the three axes together, z, x, and y. 4 ways, 4 Bell basis states, and that's how neat symmetries start to appear in this formalism. Yes, so this is how we represent psi plus. We invert x-axis, we get phi minus state. We invert y-axis. Y-axis is inverted on just on one of the Bloch spheres. We get the phi plus state. And finally, we invert all three axes on one of the Bloch spheres, and we get the psi minus state. The way how we obtain this and why this happens, we will speak about it at the end. But short description, we can empirically or heuristically, we can just rewrite each state in a different conjugate basis. Basically, in z, we usually write the states up, down, down, up in the z conjugate basis, but we can do it in x and y conjugate basis, and then we can look at what are the relationships between the arrows, these arrows representing the state there, and we can come up with a formalism. And more exotic but still maximally entangled state like this can be represented also by local rotations of single Bloch sphere that corresponds to some entangled state. We just know what are the rotations to move from one entangled state, for example, psi minus, to more exotic states, and then we can get them. You see, although so here the names of the axes are switched, so it's still a left-handed coordinate frame, although from the first sight it might not look like that, but it's still a left-handed coordinate frame on one of the Bloch spheres. So let's look at how we can obtain all of the states, all of the maximally entangled state from just having a single representation of a single state. So we have our phi plus state where y-axis is inverted. This is phi plus state. If we rotate the second Bloch sphere in this xy plane, as we rotate second Bloch sphere in the xy plane, you see we have rotated it by 90 degrees. We get the next state, up, up, minus I, down, down. We rotate it further, we get phi plus. Yes, phi minus, sorry. We get phi minus state. Up, up, minus down, down. We rotate it even further, we get up, up, plus I, down, down state. Yes, so we are just performing the rotation of xy plane. We're moving it around. If we want to rotate, for example, in zy plane, from this state, upper state, we can obtain the next maximally entangled state just rotating the zy plane in this way. Zy plane. I don't know whether it's seen very nice on my picture, but it's a rotation in the zy plane. In conventional language, it will be a rotation around the x-axis, but I use zy plane. And then we obtain other states, and basically all of the states that are maximally entangled we can obtain in this way. All of the maximally entangled states have their own representation here. So what is interesting with this formalism, it highlights very nicely neat symmetries of entanglement and non-entanglement also. For example, we have an arbitrary state. This is a state up, up, minus I, up, down, plus down, up, plus I, down, down. Arbitrary maximally entangled state. It has its own representation in this formalism. And by just looking at which axes are collinear with each other. For example, on the first Bloch sphere, z-axis is collinear with the y-axis on the second Bloch sphere. We can tell which rotations will not change this state. So for which rotations this state will be an eigenvector. It's z cross y rotation. Yes, and looking at other collinear axes, like for example y1 and x2 axes, we get the second rotation, which is rotation for which this state is eigenstate, and the third as well. So there are it becomes evident why some states are eigenvectors of some particular rotations, and it can be done without the matrix formalism. And there are other interesting symmetries that are popping up just visually in this representation. And more on a foundation side, so it looks like entanglement has something to do with the inversion of internal coordinate axis of one of the particles. What's more interesting is that such a formalism, it conveys the main essence of entanglement. Basically, that there is a although there is a Bloch sphere for each separate particle, all of the information is held about the state is held in the relationship of the Bloch spheres, in the relationships of the axes. When you look at single Bloch sphere, you cannot say anything about the particle. It is a result of the experiment, and it is a result of this formalism. When you just look at a single Bloch sphere, you cannot say anything about the particle. There is dot in the middle of the Bloch sphere, and you cannot say anything about it. But when you only look at the relationship of these Bloch spheres, of the axis of the Bloch spheres, you can say everything about the state. So it conveys the main essence of entanglement, two-partite entanglement. So entanglement has something to do with inversion, and that's, I think, an interesting thing that gets highlighted by this formalism. And when we move from non-entangled mode to entangled mode, it amounts just to the inversion of the coordinate axis. Moreover, when I spoke about the planes of rotation instead of axes of rotation, I used the idea from geometric algebra, where they are saying that axis of rotation is well defined only in 3D, when we have a 3D space, and otherwise, if we have higher dimensional space, we need to define a plane of rotation, which is always well defined. So in this sense, we can attribute local rotations, so basically rotations of a single qubit, non-entangling rotations, to planes of rotations which are bound to the axis of only the first or the second qubit. For example, for example, let me take a red pen. Z1 wedge x1 plane of rotation would be rotating the first qubit in this way. But entangling rotations are the rotations which are of the form like this, Z1 x2 plane of rotation. So basically entanglement in our 3D description, of the Bloch spheres, entanglement is entangling operations are the operations which are defined on the plane, which are rotations in the plane that is formed by the axes of the different qubits. So basically we can take Z1 axis and we can take X2 axis and form a plane of that. Whatever the way, we cannot imagine how it looks like, but the feel of rotation in this plane is inversion. That's one of the main takeaways I want to kind of highlight. Yes, so when we are rotating in this strange, let's call it hyperplane, which spans first and the second qubit. We feel it, and it looks like inversion. And there's more sophisticated dynamics actually, because the arrows of the state vector, they have to be reduced and a little bit and rotated as well sometimes, and sometimes they are eigenvectors, sometimes only one qubit turns. But when we are speaking about entangling rotation, it's always a rotation in the plane of this form, of the form where it's formed by axes of different qubits, and it always feels and looks like inversion of the coordinate axis of one of the Bloch spheres. So it's always movement from the representation of two Bloch spheres being having the same handedness or non-entangled mode, to representation having Bloch spheres with different handedness or entangled mode. So that's about it. If I would be very happy if you send me questions. I would be very happy to answer them via this email. It's also on the poster. You can also write in the comments in this video, or any other way you can contact me. It would be interesting to discuss with you what you think about it. There are still interesting moments to be understood, but I think this geometric representation, it just so vividly shows some of the symmetries, and so vividly geometrically gives a geometric interpretation for entanglement, that I think this is just a very, very interesting way to represent two-partite entanglement, and think about rotations and think about operations which are entangling as rotations in this strange hyperplane spanned by axes of different qubits. Thank you very much for your attention, and I hope to see you next year in Vaxjo. Thank you.